Hello everyone. The goal of this video is to understand the fine structures and the G-man splitting. But before understanding them, we need to talk about some of the notations we would be using throughout this process. And the notations are, whenever you see capital L, capital S, capital J, you must think of them as defining the state of an atom as a whole. But if you see small cases or lowercase letters, you should always think of them as they are stating the state of an electron. Okay, we have a defined way to explain and to write the spectral term, and that definite way is this: R on the left superscript and J on the lower left, on the right subscript. Okay, so what does these means? The value r, or the quantity r, is called multiplicity, and multiplicity is given by 2s plus 1. S here represent the spin angular quantum number, and the spin for the electron is half. So actually not for atom but for electron is half. Yeah, half. So for electron, this multiplicity is always 2. Okay. Now this J here is given by L plus minus S, and this J is called total angular quantum number, or total angular momentum quantum number. Total angular momentum quantum number. L is orbital quantum number, orbital angular quantum number, and S is spin angular quantum number. Okay. Small l is orbital quantum number, small s is spin quantum number. You should understand the meaning of those letters. Now let's suppose, so up to now we have said that for any spectral item, any spectral term, we would use this. Any spectral line, we would use this denotation. What does that mean? Before that, L is 0, it means atom is at s sublevel or subcell or orbital. If L equals 1, it means at p orbital, L equals 2 means d orbital, and L equals 3 means f orbital. Let's suppose a spectral line is formed when electron jumps, or electrons comes back from p orbital to the s orbital. How do we write the spectral line, and how do you write the spectral line? That is spectral line. So this is our case. Now this p orbital, as you can see, is given by L equals 1. For it, L is equals to 1. Spin for electron is always half. So our J would have values L plus minus S, 1 plus half, that is 3 by 2, or L minus half, that is 1 by 2. Again, if you see here, for s orbital, L equals 0. Please don't be confused with orbitals and the angular quantum numbers. Okay. So L equals 0 means, now S for electron is always half. So our J would have value given by L plus minus S, L is 0 plus minus half, so we will only have one value, that is half. So this spectral line where an electron comes back from p orbital to s orbital is represented as r as, not s but yeah, r as j. Wait a second, not s. Okay, I think it's r, and according to the value of s we would change it. Now since it's a p orbital, we would say p and j to r s j, since it is going to be s orbital. So what is r here? Multiplicity always is 2. J has two values for p. One is 3 by 2 and value of it is half. Yes. Again another one is 2p 1 by 2 and 2s 1 by 2. So that means this spectral line actually is split into two spectral lines. First one, no, what does it mean? Yeah, means that this electron coming from p orbital to the s orbital will give us two, or we can say that this spectral line would split into two spectral lines. First one given by this value, second one given by this value. So we would get two spectral lines. First spectral line is defined as this. Second spectral line defined by this. Yes, this is it. Okay. Now there are some nuances you should take care about, and they are called selection rules. That means all the spectral lines that you see here won't be considered to be existing in the real life. And to understand which of the spectral line actually exist in experiments, you need to understand some selection rules. Now, an electron jumping from one energy level to the another level. So yes, for the transition of an electron between the two levels are governed by certain rules. They are called selection rules, and they okay. Yeah, actually there are three selection rules. First one is delta L must be plus minus 1. Okay, first one is delta L equals plus minus 1, delta J equals plus minus 1 or 0, and delta S is equals to 0. For our spectral emission, for which, if you see, let's suppose in this example, we had 2p3 by 2 and 2s 1 by 2. Let's suppose another spectral line, which is, I think I should make another shell here, and this can be written in the form of 2s3 by 2. Yeah. So here, if you see, this is J, right? Now for this, J has 3 by 2 value and it has 1 by 2 value. Minus 1 by 2 would give us 2 by 2 equals 1. That means plus minus 1. So this one, yeah, this spectral line exists in real life since it follows this selection rule, or this satisfies this selection rule. Similarly, if you see S, we know that its spin was half here and half here too. That means change in spin is 0, and that is also satisfied. Similarly, if you see delta L, now what was L for here? L was S. That means L was 0, S orbital. L was 1, P orbital. So 1 minus 0 is 1, plus minus 1. So all the three rules are satisfied by this particular spectral line. So this is a very uh, probe to be seen in experiments. Similarly, if you see this one, 3 by 2 minus 3 by 2, j equals 0. This is satisfied. This is always satisfied for this, and now this is also satisfied. So spectral lines would be seen, or those spectral lines would be seen in an experiment for which all these three selection rules are satisfied. If any of these selection rules are not satisfied, that means that spectral line is not real. It's a hypothetical, it's a theoretical result that it is possible, but it is not so possible or so probed that it would be seen in an experiment. Okay, so these are the selection rules for the existence of spectral lines. Now, there are other allowed transitions, and there are other shortened rules which are called intensity rules. Okay, that means which of the spectral lines would be intense, which would be less intense. These are also governed by something called intensity rules. And so intensity rules, if you want me to write, are these. So for which those spectral line for which change in L is equal to change in J, those, okay, I don't think you can see it. Yeah, those are the most intense. These are the most intense spectral lines. Similarly, those spectral lines for which L decreases, the value of L decreases, these are more intense than those which L or J increases. That means if you see this spectral line, you can see L equals 1 to L equals 0. So it decreases, right? So this is more bright, or this is more intense than those. Okay, we don't have that right now, but then for those spectral line for which L increases. Okay, we don't have that in our particular example. Do we have this criteria? Let's check. So change in L is 1, change in J is what? 3 by 2, 3 by 2 minus 1 by 2. 3 by 2 minus 1 by 2, yeah? Yeah, so this is also 1. So that means this spectral line is the most intense one, because this satisfies this intensity rule. It doesn't satisfy this rule because it is 0. So del J is equals to 0, but del L equals 1. So del L is not equals to del J. So it will be intense, but not uh, intense, or not more intense than this one. This is the most intense spectral line in our case, in our particular example. Now we will have different one according to the examples that we have taken. So this is it. These are the intensity rules. Now let's directly go into the fine structures of sodium D lines. Okay, so you should be very uh, clear about one thing here. That is, now we have, okay, I realized that I have been using the word subshell and orbital interchangeably and that is wrong, because if you see, for s orbital, sorry, s subshell, we have one orbital. For p subshell, we have two orbitals, and for d subshell, we have three orbitals. And similar way, is it three or is it five? One, two, three. I think it's five. Okay, but you got the point. I really don't know how many orbitals are there. So let's suppose, so that means each subcell has different orbitals. Uh, Wait a second, let me check. Yeah, it's true. The D subcell has five orbitals. So, and it has three orbitals. P subcell has three orbitals. So different subcells have different number of orbitals. So we can't say the words interchangeably. Okay. Now, another thing you should understand, that whenever we are talking about fine structures, you shouldn't think of them as the transitions that you see in the case of absorption or ionization. Okay. Now, the emission diagrams and the spectral line diagrams are different things. You know that the fine structures are not due to just the spectral lines. It's due to the spin orbit coupling. And because of the spin orbit coupling, these this shell can't show, these kind of diagrams can't show the spectral line diagrams. For the spectral line diagram, you should consider these things. So whenever you are forming, or whenever we are drawing a spectral line diagram, you must understand some of the basic things. First one, doesn't work. We can't show a spectral line in that diagram. Now what we do is we form the ground level. Let's suppose we have an example. Now we are talking about the spectral line of sodium D line, right? So if you see the sodium, it would have 11 electrons, and last electron would only take part in the spectral emission, right? Now let's suppose that that electron on the s subcell, s subcell can go to either p orbital or p subcell or d subcell, okay, and different orbitals. So if you try to uh, keep account of all those spectral lines from each of those orbital, it would be very hard for us. It would be tedious for us. That's why you don't have to do that. You don't have to do that. But for understanding the spectral line, you just say that from this ground level, I don't know where it went. I don't know where. But I'm not interested in where it went, but I am interested from that from where it came to the ground state. And that I didn't have to for that I didn't have to think much, but just follow this. If I follow this, now we know this the ground level is S or S sub cell. That means L equals 0. And when L is equals to 0, J would have a value of half. So I can say it's this component. And here, if I put the value of maybe L equals 1 for the p orbital, sorry, p subshell, let's suppose uh, the electron went to the p subshell, then if that spectral line, if I want to show that spectral line, then what I would do is I would write it as 2s 3 by 2, or I would have 2s 1 by 2. So see, even though we had three orbitals in the p subshell, but there will be only two conditions, or there will be only two types of spectral lines from for the emission of electron from p orbital, p subshell, just s subshell. Okay, and that is why I always interchange these subshell and orbital. I'm very sorry for that. That's wrong. So What I said is that I don't have to worry about that. I can just see which of the orbitals are possible, which of the spectral lines are possible by using this golden thing. Okay, so one of the spectrum is this, the spectral line is this, one spectral line is this. Now sometimes we can consider other emissions too. For example, we can consider let's suppose it came from D, spectral line came from D subshell. If that is the case, then it becomes L equals 2. Again, this D would have two components. First one is 2 3 by 2 and 2 5 by 2. Now you can see the spectral lines, two spectral lines from here to here. Okay, now again, if I consider that I have electron coming from F subcell, then that would be that would L would be 3. So I'll have the value 3 plus half would be 7 by 2, 7 by 2, 2F 7 by 2 to 2F 5 by 2, and we will have 2D 5 by 2, 2D 3 by 2. So we'll have a lot of spectral lines. So that's why now all of these spectral lines won't be visible for the experiment in the experiment. That's why we have the selection rules. Now we have the selection rule that these are the selection rules. So if you see here, L equals 1. L equals 1 is P, L equals 2 is D, L equals what? L equals 3 is this, F subcell, F subcell gas. Now S is L equals 0. If you see this, all the spectral lines from P subshell to the S subshell are only feasible from this selection rule. All the other are neglected from this selection rules. So these won't exist in experiment. Now these two lines which I had done previously are only feasible for the experiment, and these two lines, the smaller line or shorter line is called D1 and this is called D2, and these D1 and D2 are the fine structures what do we say it? Yeah, fine structures of sodium D line. We have two values. Now the shorter one is 5890 angstrom, and this longer one is 5896 angstrom. Okay, so I think you understood. If you don't, I am going to revise this again, don't worry about it. Okay, so we learned some things. First thing we learned is that whenever we are talking about spectral lines, we don't think about that diagram, never, because due to the spin orbit coupling, these orbitals won't be the same as we have here, and these orbitals, all of those orbitals even won't even work or won't even be used. Again, even if we consider those by using that formula given by this, then that doesn't mean that all the spectrum would be feasible. We have to use the selection rules to see which of these spectral lines are feasible. Okay, so what do? You first use this formula and see how many spectrums are possible if an electron from some of the higher energy comes to the lower energy, and see by using the selection rules which are actually feasible, and those remained after these two filters are actually the spectral lines that we see in our experiments. Okay, let's talk about fine structures of S alpha line. Now we know here that the S alpha line is a member of Balmer series. That means it happens when an electron from n equals 3, principal quantum number 3, or we can say third cell, when an electron from third cell jumps to the second cell, or any high, or we can say from any higher. Okay, so we know that the Balmer series means any of the electron jumping from any of the higher, like higher atoms, higher levels into this second level. These are called the Balmer series. Now here, as alpha line is produced particularly when the electron jumps from third energy level to the second energy level. Okay. Now n is defined here. That is the principal quantum number is defined here, and it's a one electron system. That means since we are talking about hydrogen, now there is only one electron, and only one electron will govern the entire atom. Okay, so it is different from the sodium case. So here we know that n is equals to 3. That means now we know from the quantum mechanical rules that L has value of n minus 1, and n minus 1 is 2 here. N minus 1 is 2. Similarly, it goes from n equals 3 to n equals 2. So n equals 2 means L 2 minus 1 becomes 1. So we have values L equals 2 and L equals 1. If you want to see it, you can see it right here. So L equals 2 for an electron means L equals 2 for entire atom if it's a one electron system, and L equals 2 means we have two values for Z, 5 by 2 and 3 by 2. Similarly, L equals 1 for the electron means L equals 1 for the atom if it's a one electron system, and J would have values 3 by 2 and 1 by 2. So that means now this L equals 2 means it's a D subshell. So we write D, and we have 5 by 2 and 3 by 2. So 5 by 2 and 3 by 2 have two components here, and we would get four spectral lines. One is from D 2D 5 by 2 to 2P 1 by 2. Another is 2D 5 by 2 to 2P 3 by 2, and others are 2P 3 by 2 to 2P 3 by 2, 2P3 to 2D 3 by 2, from 2D 3 by 2 to 2P 1 by 2. So we have four of the spectral line possible theoretically. Now let's see, by using the selection rule, are these all spectral line visible in the experiment? To see that, selection rules are, now this is always satisfied since it's a case of electron. Now delta J equals plus minus 1. Let's see this. Delta J equals plus minus 1. If you see this, 3 by 2 minus 1 by 2. That means, which one? This one. Okay, this one. If you see this, it's 1. So this is feasible by this selection rule. If you check this rule, L equals 2, L equals 1. So for all of these spectral lines, this condition is also satisfied. So this is the only selection rule which is actually going to have give us results. Now okay, so it says that this is possible. Again, if you see this one, 3 by 2 minus 3 by 2 gives us 0, and we know 1 and 0 are possible, so this is also possible. If you see this one, 5 by 2, 5 by 2 minus 3 by 2. Okay, this is also possible. And let me check this one, 5 by 2 minus 1 by 2. Okay, okay, not okay. This one is not actually uh, same, or this is not satisfied. This is not satisfied for this line. If you see this, we have L equals 2 minus L. No. Wait a minute, wait a minute. We have 3 by 2 minus 3 by 2. Okay, J is not 0 here. J is just plus minus 1. If it's a plus minus 1, then this is not satisfied. So this spectral line won't be here. This is correct and this is not. Yes, because 5 by 2 minus 3 by 2 would be 4 by 2 and it would be 2. Now we can't have value 2. So only the two spectral lines. These spectral lines are possible and these are called H alpha. Actually this is just one line and this is split into two, which looks like this. And these are the fine structures for H alpha line. So this is it. Okay, you can understand the fine structures, and I hope that from these examples you have understood the phenomenon quite well. In the next video we will see G-man effect in much detail. Thank you so much for watching this.